Hey there everyone, welcome back to my YouTube channel. So guys, this is the continuation video of feature scaling techniques, and in this particular video we'll be discussing about normalization, min-max scalar and robust scalar. So in my previous video I have already explained you all about feature scaling, and also I have discussed about standard scalar, which is nothing but standard scaling. Even the coding part is available there, you can have a look there. That is part 1, and this is part 2 of the normalization, feature scaling, and this is a continuation video. If you have not watched that, watch that and come here. That particular video link will be in the description. So guys, now let's not waste our time, let's dive into the computer screen. Before that, if you have not subscribed the channel, do subscribe the channel and on the bell notification. Now let's dive into the computer screen. So guys, as I said in my previous video also, this particular article link will be available in the description. You don't need to make any notes. You can have a look on this video and just understand the coding part and everything. Even the collab file link will be in this video description only. So let's continue with normalization. Normalization is the process of transforming the feature variables in a dataset into a common scale, like typically which is in the range of between 0 to 1 or -1 to 1. The objective of normalization is ensure that all features have similar scales, which helps us to prevent some certain features from dominating the model process. It's nothing but in normalization, whatever features we are having, we will be making sure that it will be laying between 0 to 1 or -1 to 1. And this is mainly done because we don't want our model to like get dominated with other features. Like if the sparsity is high, if the data sparsity is high, then we don't want the model to take more time in training, and we don't want it to get some like model failure, running failure, or else the prediction failure. So we use this particular normalization for that, so that the training process should be smooth. So in the video 6, I guess in the 6th video of machine learning, we have discussed about feature scaling, right? In that article also I have explained you all clearly about feature scaling. So if you have not watched that, you can have a look on that particular video also. So if you see here, this is the actual data, normal data with high sparsity. You can see here the points here. This one, they are very high sparsity. If you see, they are not in a linearly, like they are not linearly available. They all are non-linearly available. So what we have done after normalization, you can see here all the data are lying between 1 and 1. Here 1 and 1, 0, 1 and 0, 1. So you can see here now they are perfectly like available for us to perform the model training. And after standardization, if you see normalization, what it does, it normally brings between 0 to 1 or 0 to -1, -1 to 1. But when you perform standardization, you can see here it will go with 1, even -1 also. Again it will go like this also. It's a kind of four-side graph, and this will be make sure that it will be in a one-sided only. All are scaled between this one side graph. Now let's go further. You can see here this original data. This is the original data. You can see here 180, 50, 0, 50, 100, 150. It's a kind of like high. The data dimension or a sparsity is a kind of high. You can see here somewhere some values are at 25, and these all are at very low. So it's model training will take more time if you see this data. But when you perform min-max scaled for this, you see that there is no much improvement. But you can see here this is the minimum scaled, sorry, maximum scaled, and this is minimum scaled. 0, 1, 0, 2, like this is a kind of not much performance. But when you see with the standard scale data, mean and mean deviation, a kind of this particular data, you can see this is the 0 and -3 and +3. You can see here a kind of this data, it is getting perfectly standardized, or you can say scaled using different techniques. Using min-max scaling, you can see here this is the difference, and using standard scale, this is the difference. So that particular image is also from Google only. Different types of normalization methods, which are nothing but min-max scaling, mean normalization or normalization scaling, and robust and maximum absolute scaling also. Min max scaling is also known as min max normalization, which is specifically ranging between 0 to 1 or minus 1 to 1. So it rescales the data. So whatever data is available, right, whichever high sparsity data also, it will just rescale the data and bring into a common line. You can see here. So mathematical formula for that, it will be like x normalized, this is a variable, is equals to x minus minimum value min of x divided by maximum value minus minimum value. So this is the formula to calculate that. I'll show you all in the coding point also. When it comes to minus 1 also same, like a kind of 2 into, you'll be adding 2 into here and your minus 1 here. Simple and intuitive method when you use min max scaling, preserves the relationships between data point, suitable for algorithms that assures data with a broad range. Disadvantage is sensitive to outliers as they can affect the range of the scaled data, may not work well with the data that does not have clear boundaries. So these are some of the disadvantages. If the clear boundaries are not defined, it doesn't work with the data well. So first let us perform min max scaling, then we will come back to this mean normalization scaling. So this is normalization. Let me connect to this. So some of the common libraries we need to import, which are nothing but Seaborn, NumPy, Pandas. As I told you all earlier, if you want to learn about Pandas and NumPy, link will be in the description where I have explained very detailedly about Pandas and NumPy. You can go and have a look on that. And in this particular normalization technique also, we'll be using a default data set from sklearn datasets. We already have something called as lone wine dataset, inbuilt dataset. We'll be using that. So loading the lone wine dataset, and we'll be checking the head of that, creating a data frame, and we'll be checking the head of that. The normal features, you have to create a data frame, right? So you can see here alcohol, metallic acid, and class label. So we have created this here. You can see here what is the alcohol and the metallic acids of it, and class label we have checked this. So now if you see the df.shape, even this as of 178 rows and 3 columns. Now what we have done, we have checked it with KDE plot. From SNS you have something called as KDE plot. So we have checked this KDE plot of that particular each and everything. First we have checked for alcohol, and then we have checked for metallic acid. Then we have checked the scatter plot of this both alcohol and metallic acid. We have checked the scatter plot. You can see here the data is like alcohol and the metallic acid. A kind of, if you see, try to correlate, the sparsity of the data is very high. You can see here some features are at 6, 3, very less features are here. Many features are available here, but if you see here some features which are like a kind of outliers, they are acting here. Because of this, the model performance will be very low. So now again what we have done here, we have color coded this particular things. So what we have done, 0 is equals to red, 1 is equals to green, and 2 is equals to blue we have defined here. And we have given here, assume the class label as like this x value and y value, and then we have given HUE is equals to df of class value, and finally we have given the petlet as color dictionary or color coding. And if you run this and see now you can clearly see here, after doing the color coding of 1 2 3 also, I mean 0 1 2 also labels, you can see here it's a kind of sparsity is still high. 0 1 2, why I have coded this, I have already told you all, right? These are some of the features available already. Okay, so we have just taken that for our data, I mean like a categorical data. These are the 3 features which are available in that particular metallic acid. You can see here even there is a detailed explanation. This graph is a scatter plot, and we have plotted the data points of alcohol in x-axis and metallic acid as y-axis. I have already explained you all. As we are using the class label, so we have used this, and then finally what it has happened. So the above graph gives you the insight that the data distribution is requires some transformation before applying. Now we are getting into normalization. So we have done the train test split of that particular data. If you see, same as I told you all in the earlier video also, same, there is no changes. So class label is our target variable, and then test size is equals to 0.3, which is nothing but 30%, and random state is 0. And we have taken for x train, we have taken those both columns, and x test also same, and our y train y test we have taken class label feature. So you can see here. Now from sklearn.preprocessing import minmax scalar. So we are using minmax scalar now. So scalar.fit x train x underscore train, scaled transformation of x train and x test. Then finally we are performing after fitting x train. You can see here. Now store the values of scattered data into pandas data frame. Again we have created a data frame here. So previously if you see, these are not in data frame. Let me show you all. Type of, so they are kind of numpy ND array, you can see here. Now if I remove this, like if I just give this one, and if I run, you can see here it's a kind of ND array. So what we are doing, we are again storing this into a data frame. So once you have stored them again back to the data frame, so that you don't get confused, and if you check this now, xtrain.describe and xtrain.scattered describes the same way. We are checking before scaling, this is before normalizing, and this is after normalizing. If you see here the difference, mean 0.5, standard deviation 0.2, and then your mean. Let us do one thing, let us even perform one calculation here also. I'll show you all of why to take tension. So for normalization, what we have to do, x minus mean divided by standard deviation, mean of x divided by standard deviation. It's same, right? Okay, this is for mean normalization. We will check for our min max scaling. So for this what we have to do, x minus minimum of x min, so which is nothing but, so let us take x1 is equals to, what is our x value? Let us take the maximum value only. So let us take 12 now. For example, maximum value is 14, so let us take 12 minus minimum value, min of x. So they have asked, you can see here, min of x. So min of x is nothing but 11, then divided by min minus max. So divided by, so our min value is nothing but 11 minus, so what is our maximum value? 14.8, right? So 14. Let us take. Now let's run this. So now if you see this, 15.666 is your normalized value. So I'm just giving you all an example like how you can perform calculation. So normally we can perform this with our, like, mathematically also, if I can write and show you all, but I want you all to understand it in a kind of coding point of view so that you don't feel any challenges. If I go mathematically, you will definitely get confused. So I want to explain you all in more a kind of coding point of view than mathematically. So this is a describe for before scale and after scale. You can see some differences between. So maximum value is 1 and our 75th percentile is 0.7. You can see the differences between both. I'm not going to explain you all much because in my previous video also I told you all. So you can see the differences. Now if you see before scaling and after scaling graph here, metallic distribution, acid distribution, before scaling and after scaling, you can see here they are a kind of the features are proper right now. You can see they are scaled properly, and you can see that there is not much changes in the graph also. You can see there is a kind of slightly changes, very slightly, not more. Okay, the same thing we have done for alcohol also. Yeah, same. There is no change. There will be no change in the graph of the particular data. There will be only changes with the features. Like its high sparsity. There was a high sparsity before. We have brought it very less, and we made sure that the data can train smoothly. We have just normalized it. And for mean scaling, you can definitely there is okay, scaling. You can see there is some differences. Like for alcohol and meta density, you can see here before scaling how it was a kind of like this. There is no much kind of correlation. It was very far, and it was very difficult to execute. You can see here you can see, and here. So what we have done after doing the min max scaling, you can see they are kind of correlated a bit. And again we have performed scattering of this both. You can see here before scaling and after scaling, you can see there are some slight changes. You cannot expect more changes for this because the data is very less, and I'm using just a pre-trained model to explain you all a bit better. When you are using high data and high columns, you will see more a kind of changes, and you will be seeing that there is a high impact of normalization and standardization. Now let's go with another technique, mean normalization scaling, which is also known as z-score normalization or standardization, where the data have a mean of 0 and a standard deviation of 1, and it is particularly useful with dealing the data in the flow of Gaussian distribution. So why we use mean normalization scaling? Mainly for distributing the data in Gaussian format. So x underscore normalized is equals to x minus mean of x divided by standard deviation. This is a kind of standard scalar formula only. You can see here. To just get the Gaussian distribution, we use this. Make data compatible with algorithm, same, reduce sensitivity of outliers, okay, preserve the relativity distance between the data points. So same, the advantages and disadvantages are of kind of same. You can have a look on that. Now let's go with the coding point for this also. So for normalization, you can see here from sklearn.preprocessing import normalizer, and for this we have again done the same, like xtrain we have taken already, and we have separated it. Fit transform we have made it, and finally again those will be, I told you all right, they all are in a kind of now array format. Now again we have written a code to bring them into a data frame format. Now if you check this np.round, again we made it round. Now we have checked the description for this. You can see here, if you see the describe, you can see here this is the describe of that particular data. I'll explain you all a bit with graph. You will understand a bit more better. Same graph before scaling and after scaling, you don't see much changes, and you can see that here 0.40 and 15. Now it is between -2 plus 2 here, and 0 and 1.14, sorry 1.4. Same for metallic acid also, between -2 and 1.2, 0 -2 and 1.2, and here also you can see this before scaling and after scaling. So it has been scaled. You can see the differences for both. That's what you have to see, this x-axis and y-axis numbers to see and identify the differences. Now let's go with robust scaling. Let's complete this soon. So maximum absolute scaling also it's same as it's same. You don't have changes in this, and this is the formula for that. X normalized is equals to x divided by maximum of x. That's all. Advantage, disadvantages are same. So robust scaling, which is nothing but IQR method. IQR is nothing but interquartile range. So it is mainly used, or else you can say why we mainly use this is to find out the interquartile range. IQR in a sense, see, let me explain you all. There is a formula for IQR actually. X minus median divided by IQR of X. Interquartile range, which is nothing but middle 50% of the data. And there's another formula for this, I guess. Let me show you all. I guess I have not mentioned here. IQR formula. There is actually another formula for this IQR. From, yeah. So let me show from ClueMath only. It's fine. So IQR formula is nothing but Q is equals to Q3 minus Q1. You're getting my point. Interquartile range is equals to upper limit by lower quartile, upper quartile by lower quartile, which is nothing but, if you see the describe here, so upper quartile is nothing but the 75th percentile minus your 25th percentile. That is IQR formula. I guess I have missed that. Let me try to show you all a bit more detailing. Yeah, in this it will be good. So Q1 and Q4 you can see here, and this is your 0.5, this is your data, and you're just scaling it between 25th percentile, this side 25th percentile and 75th percentile, you can take it. So whatever 50% data you have in between, right, that is your IQR data. You can see here 50% of your data is your data using you're using that particular data. So IQR formula is nothing but 75 minus 25. You can easily remember this, which is nothing but Q3 minus Q1. So let me run this and show you all. Formula is done and advantages and disadvantages are same. Let us work with this particular coding part now. So robust scalar from preprocess import robust scalar, or else you can manually write the IQR formula here and you can divide the data. So again extract scaled and xtest robust scaled. Then we have used it again for describe method. Same, whatever we have performed for the above operation, same, no changes. And after rounding off, you can see here maximum is 1.3 and 75th percentile is 0.5 and 0.8. Mean is minus 0 for alcohol and 0.3 for metallic acid. So figure, if you see here, alcohol and density, you can see the features minus 2 and 1.2, 1.4. So it has been scaled. You can see the x-axis and y-axis for difference before scaling and after scaling. Metallic acid also before scaling and after scaling. You can see you. So finally, then what I have done, like I have printed all the scaled plots here, I guess. Yeah, all the scaled plots are available here. You can just compare before scaling and after scaling, mean normalization. So this is nothing but metallic acid distribution after min-max scaling, this is, and after mean normalization, this is, and this is after robust scaling. You can see that there is a kind of not much more differences are not there. You can see here. So after min-max scaling, you can see the features lie between 0.2 to 1.2, and after mean normalization 0 to 0.5, and after robust scaling minus 1 to 3. That's all. There you cannot see that much of difference, but yeah, it helps us in scaling the data. That's all. When you have high data, you will see this. You will see the advantage of using this particular normalization and standardization. So guys, that's all for today's video. Do like, share and subscribe the channel, and let's continue with the next topics in our upcoming video. Bye bye.